Okay, these are the short answer questions from the practice problems from Unit 2. 14 gives you this picture here, two masses hanging over a pulley. So we're going to draw a free body diagram. One for the 5 kilogram mass would look like this. It's got mg pulling down, and it's got tension pulling up, and the tension will actually be a little bit bigger than the mass because it's going to go this way. For this 7 kilogram mass, you have a free body diagram that has mg pulling down, which is going to be bigger than the tension force pulling up. And then for the system, you represent the system as a dot, both masses. There's only two opposing forces. One is mass times g, I'll call it m2g. And I'll call this first one m1g, where it's going to be the mass of 5 kilograms. So it's going to be 5 times 9.8. I'm sorry, the net force in this case is equal to the bigger one, which is m2g. I'll call this 2 in this one, minus the smaller one, m1g. So that's the mass of the system, which is 12 times the acceleration of the system, equals 9.8 minus mass 1, which is 5 times 9.8. And then we're going to divide both sides by 12, and that gives us an acceleration of 1.63 repeating meters per second squared. Okay, the next problem gives us a force F1 with a magnitude of 57 newtons, another force with F2 with a magnitude of 57 newtons, and then F3 has a magnitude of 57 newtons. And the angles here are 30 degrees. So then we can make triangles out of this. And we know these are special right triangles, where if you use your special right triangle values, this is x, this is twice that, I'm sorry, this is x, this is twice that, and this is x times the square root of 3. So basically that means that this is 57 divided by 2, which is 28.5 newtons, and this is 28.5 newtons. And it doesn't matter what these are because they're obviously equal and opposite because they're the same. So 57 divided by the square root of 3 would give you I'm sorry, 57 divided by 2, and then whatever that is times the square root of 3 would give you this value. But it's equal and opposite to this one, so they're going to cancel. And you can tell that, so if you add the x's, the only two x's are these, which are equal and opposite, so those cancel to 0. And the y component, you add this 28.5 to 28.5 up. So there's two of those going up. And then you've got one going down at 57. Well, that adds to 0. So the x and the y components both add to 0. Therefore, the net force is 0. This thing's in equilibrium. Okay, this next problem is pretty easy. It says a mass of 2.7 kilograms is released with a speed of 2.9 meters per second. I wrote down the problem, drew a picture. If you draw a free body diagram, there's only one force acting on this, which is friction. So that force of friction is equal to mass times acceleration, like all forces, and they give us the mass of 2.7 and the acceleration of negative 0.27. So multiply that, and that gives you your answer. Negative 0.729, and that's meters per second squared. I'm sorry, that's newtons, because that's a force. So that was pretty easy. They give you mass and the acceleration, so you can just do MA. I don't know why they give you initial velocity, maybe to throw you off, but that was pretty straightforward. Okay, so for the next problem, we've got a force pulling down, causing this girl to accelerate down the hill on her snowboard. So we can break this into two components. I'll call this F sub x and this is F sub y. And we can draw a free body diagram then for her basically at this point. Portion of her weight's pulling her down the hill. A portion of her weight's pushing her back up the hill, which would be friction, force of friction. So her net force is going to be equal to the bigger force, which is obviously that portion of her weight right there, subtract the friction force. So that's what we're going to fill out. We need to find this. This is a 25-degree angle, so 90 minus 25, you do 65. So that's a 65-degree angle. So if I want to find this portion, I would do adjacent over hypotenuse. So I do cosine of 65 equals adjacent over hypotenuse. Multiply both sides by mg. That gives me f sub x. So her net force is equal to mg cosine of 65 minus the friction, which is mu sub k times the normal force. But the normal force I have to find, the normal force I can find is right here. If I do sine of 65 equals opposite over hypotenuse, multiply both sides by mg, there's my normal force. So I can plug that in right here then. So I have mu sub k times mg sine of 65. And my net force is equal to mass times acceleration. We want to find this acceleration right here. I can cancel a mass out of each of these because there's a mass at each one of them. So acceleration equals 9.8 cosine of 65 minus mu sub k, which they told us was 0.15, times 9.8 times the sine of 65. That gives us the acceleration, which is 2.8 meters per second squared. And if that's the acceleration, then they said 7 seconds later how fast is she going, so we can just use the definition of average acceleration, which is change in velocity over change in time. So we have 2.8 equals the final velocity minus the initial velocity. The initial velocity is just 0 though, divided by the time of 7 seconds. So we'll just multiply this by 7, and that gives us about 19.7 meters per second. Okay, this is definitely the hardest problem. We're going to have to break this up into components. So, got a component pulling this way, a component pulling this way. I'll call this 1, this 2, and this 3. Give these names. I've also got a component pulling this way from this tension to break one up into its 2 components, and a component pulling out. Alright, so these two are equal and opposite. I don't know what they are. Actually, I'm going to call this tension in the first one. I'll call this tension in the second one and tension in the third one to give these variables. I actually don't even need a variable for that because I know what that quantity is. I know what that force is. Now, I'm going to have to set up a system of 2 equations with 2 variables for this one. So I'll do the x information first. So I'll do cosine. I'll call this x for right now just to show you that this is cosine of 27 equals adjacent over hypotenuse. Multiply both sides by t sub 1, and you get this right here. So I'll call that t sub 1 cosine of 27. The same thing happens over here. This would be t sub 2 cosine of 45. So one of my equations then is t sub 1 cosine of 27 has to be equal to t sub 2 cosine of 45 because these have to be equal and opposite if this is in equilibrium. And then the other equation comes from the y. This is now t sub 1 sine of 27. And if you're not sure, do sine of 27 equals opposite, I'll call that y for right now, over hypotenuse. Multiply both sides by t sub 1, and you'll find out that this is t sub 1 sine of 27. And similarly, this is t sub 2 sine of 45. And so if I add these 2 vertical components up, they have to equal the downward component. So there's my second equation, t sub 1 sine of 27 plus t sub 2 sine of 45 has to be equal to this mass hanging down, mg, so that'd be 285 times 9.8. So there's my 2 equations with 2 variables. I'm going to substitute, so I'm going to divide both sides by cosine of 27 here, and I'm going to substitute then t sub 1 in right here. So t sub 1 is going to be this right here, which is t sub 2 cosine of 45 divided by cosine of 27 times the sine of 27 plus t sub 2 sine of 45 equals 285 times 9.8. So I'm going to have to multiply this number out and then add it with this number and then divide to the other side. So it's just solving with algebra now. But if you do that, you'll get, and I've practiced that for sure, it's a little tricky with these numbers, but you'll get t sub 2 equal 2,616.6 newtons. And then obviously, just plug this back in. We know what the tension from this one is. That's just, so I'll call that t sub 3. That's just 285 times 9.8, which gives you 2,793. And then the tension in the first one, obviously you're going to plug in t sub 2 up here. So multiply by cosine 45 divided by cosine 27, and that will give you t sub 1. 2076.6 about. So there's your three tensions. Hope this helped.